So far, all the algorithms we have studied are sequential algorithms. That is, we specify a sequence of steps, and each step consists of a single operation. If we want to get the result in a better speed, one direction is to design a faster algorithm that runs sequentially. And another direction is to design algorithms that specify not a single operation but multiple operations on each step. So we can run them on parallel computers. And that's why they are called parallel algorithms. When we talk about parallelism, there are two directions. One is the machine parallelism, which concentrates on hardwares such as the processor parallelism and pipelining a very long instruction word, VLIW. The other direction is parallel algorithms, which is our topic for today. And to describe a parallel algorithm, we must use some models. Here we're going to introduce two models. One is the parallel random access machine, PRAM. It's the earliest and best known model of parallel computation. And the other is work depth, so-called WD model, which is basically equivalent to this PRAM. The point of these models is to give a proper level of abstractions for designing parallel algorithms and reasoning about their performance and correctness. Different models may affect the programmer's view on the way they design algorithms. So basically, you just design an algorithm for some model, like the work depth or PRAM model, then use the algorithm to develop a computer program in some appropriate language. So the machine software will later take your code and translate it to result in an effective use of a machine. First, let's take a look at this PRAM model. In this model, we have n processors and a shared memory. And all the processors are having unit time access. Access means read, write, or some computation. And we assume that each operation takes a unit time. An instruction like this, we say on processor I, we assign A plus B to C. It means that the I's processor would read A and B from the shared memory. That is, each time to copy a shared memory cell into one of its local memory registers and do the computation A plus B and finally write the result back into the shared memory. And if we write this, say for each processor I, where I is between 1 and n, let's pardo. Assign B of I to A of I. That means we're going to let processor P sub 1 assign B of 1 into A of 1. Processor P2 assign B of 2 into A of 2, and so on. All these operations are performed concurrently at the same time. So this pardo is the keyword. It means get it done in parallel. But one problem with many processors working at the same time is that, it'd be okay if all of them are reading from the same location. But what if they're trying to write into the same location? So to resolve access conflicts, there are three commonly used rules. One is EREW, means exclusive read, exclusive write. It means at most one processor is allowed to read or write to a location. CREW means concurrent read, exclusive write. It means reading is okay, but writing is not. And the third one is CRCW. It means concurrent access is allowed for both reading and writing. And for CRCW, we have again 3 rules to choose from. One is the arbitrary rule. It means that we just arbitrarily select a processor to have the access. Another one is priority rule. That means we always select the one with the smallest number. Okay, and the last one is the common rule. That means we allow all of them to write only if they are trying to write the same value. Now we need some examples to help us understand this. Okay, our first example is quite simple. It's about summation. Given n numbers, and we're supposed to output the total sum of those n numbers. So on the sequential machine, this is trivial, right? A very simple loop will do. And the time complexity is what? Linear, right? Big O of n. Now let's see how fast it can run on a parallel model. For example, say if we have 8 numbers given to 8 processors. First, we assign them to 8 locations in the memory in one step. All right, and we name these locations B of 0i, where 0 is the round number. We're going to go through several rounds, and this is the round 0. Then round 1, let's add them pair by pair. So the first 4 processors are working in parallel, while the other 4 are doing nothing actually, to say stay idle. Then write the results to 4 locations, and we denote them by B of 1i. Okay, where 1 stands for the round number. This is round 0, this is round 1. And then continue in this pattern. So next, we're going to have 2 processors working, and finally 1, right? And so what is the formula here? We see that this is calculated from bottom up, all right? So this is the 2 numbers on the previous level. And notice that this is a perfect binary tree, right? So the relationship between this node I and its children is this. Left child is 2i minus 1 and right child is 2i, right? Okay, now let's try to describe this procedure in pseudocode. Step 1, we're supposed to assign each a of I to b of 0i. It's the zeroth round. And this is Pardo. It takes only 1 unit time to get everything done. All right? And then still, inside this Pardo, we have this for loop for the rounds, right? H corresponds to the number of rounds, right? And for H equals 1 to what? So what is the upper bound for H? It's just the height of a perfect binary tree, right? So that's log n. And for each round, only some of the processors are working. Others will stay idle, right? And at level H, what is the upper bound for I? At round 0, this is going to be n, right? At round 1, it's going to be half of n. And every time, it will be reduced by a factor of 2, right? It's divide n by 2 and by 2 and by 2. Eventually, when it gets to 1, we get the final answer, right? So what is this upper bound in general with any h? That's n divided by 2 to the power h, right? Okay, and finally, there's only one processor that contains the final result. So for the rest of the processors, they will stay idle. And for this one, we just output the final result. All right, so in total, how many rounds do we have? Log n plus 2. So there are log n plus 2 rounds. And each round takes a constant time. And therefore, the time complexity is what? It's just big O of log n, right? So this is the PRAM model. So this axis corresponds to the number of operations, and this direction corresponds to the runtime. Okay, and it allows P instructions to be performed at each time unit. Right, and each processor takes one instruction, no matter what that instruction is. Even if it is stay idle, it is an instruction. And this is called a round with P processors. So round by round, we solve this problem, and the time complexity is just the number of rounds. And this is called the standard PRAM mode. But the reality is that during each round, only part of the processors are actually working. So this standard mode has a few drawbacks. One is that it doesn't reveal how the algorithm will run on PRAMs with different number of processors. That means from this description, we cannot tell how the number of processors can affect the performance. What if we add some processors in? Will it run faster? Or what if we take some processors away? Will it run slower? So on the other hand, if we want to be more specific, if we want to fully specify the allocation of instructions to the processors, it will require a level of detail which might be unnecessary. So the bottom line is that we need a better model to be more specific, and at the meantime be sufficiently abstract. So work depth model is actually another presentation mode of PRAM. This is the pseudocode for solving the same problem but from another point of view. Notice the difference here. We have several pardos. Okay, step 1 is the same. We assign each number to a location, and this is pardo, so it takes only 1 unit of time. And then round by round, for each round, when h goes from 1 to log n, we will call pardo to do the calculation only for those processors that are actually working. And finally, since there's only one processor, we just for I equals 1, let's call pardo and do the output. Okay, so this is the figure corresponding to the work depth presentation. We start from n processors, and then half of n processors are working, and so on and so forth. Right? So this figure, it means this model better reflects the reality, the real workload. Right? So in general, the WD mode also solves a problem round by round. However, each round may have different number of instructions. But notice here, no matter which model we use, the time complexity looks the same. Both big O of log n, right? So what's the point of specifying the different number of processors? Well, in the world of parallel computing, there are actually two factors we must consider. To measure the performance of a parallel algorithm, we consider both the workload, that is the total number of operations denoted by W of n, and the worst case runtime denoted by T of n. And the reason we must take the workload into consideration is that it's related to the power taken by the processors. There's no free lunch after all, right? So if there's a project that if we hire one worker, it will take the worker 5 days to complete. So we must pay the worker for 5 days, right? And if we hire 5 workers, we might be able to have it completed in 1 day, but still we have to pay 5 workers. So workload is the amount of work we have to pay for. So when comparing the performances of different algorithms, we usually consider one of the following. First is the workload and the runtime, simply compare them. Or the workload divided by the runtime, that gives the number of processors required, right? And the runtime on the PRAM. Or the workload divided by the number of processors, where P is no more than the normal requirement of processors. And that is, if we use less processors, how much time will it take? Or W over P, that gives the required time with probably less or more processors, plus the worst case runtime, which is the number of runs. And all these are asymptotically equivalent. So let's look back to the summation problem. What is the worst case runtime? We have done the analysis before, right? And this is totally log n plus 2. For this is log n plus 1 for input and 1 for output, right? And what is the total workload? That's the number of operations, right? And this is given by, first it takes n steps to get the inputs, right? And then step by step we do these calculations, right? So the total workload will be what? And for each h starts from 1 to some k, where k is log n, we get n over 2 squared, and blah blah blah, plus finally n over 2 to the power k, where k is just log n, plus one final step to output. And put them all together, that gives 2n. Now think about this. What is the workload if we solve it on the sequential machine? It's the same, 2n, right? Still we need n steps to read the numbers, and n minus 1 steps to sum them up, and finally 1 step to output. It's the same, right? So this parallel algorithm doesn't take more effort to get the result. The effort is the same, the workload is the same, and at the meantime, save the time. The runtime becomes log n instead of big O of n, so it's indeed better. And there is this WD presentation sufficiency theorem. It says that an algorithm in the WD mode can be implemented by any P of n processors within this given time, using the same concurrent write convention as in the WD presentation. Basically, what it's saying is that this WD mode can indeed tell the performance of an algorithm with different number of processors, and that every algorithm in the WD mode can be translated into a PRAM algorithm. So they're basically equivalent. We're not going to discuss the details, so if you're interested, you may read the reference paper. Then we're going to go through 3 examples to get more feelings about designing parallel algorithms.